Click the play button. The maglev train is the world's fastest train. It could reach a speed of 430 km per hour. Superconductors are used to provide magnetic levitation of the train. Introduction. In this lesson, you will be able to define resistivity, ρ equals Ra over L. Derive the equation sigma equals Ne squared tau over m. Explain qualitatively the mechanism of conduction of electricity for semiconductors. Understand the dependence of resistivity on temperature for metal and semiconductor using the equation sigma equals Ne squared tau over m. Know the phenomenon of superconductivity. Click on the switch. Then click on each resistance wire to connect it to the circuit. Observe the ammeter reading. Observe how the calculated effective resistance of the wire varies with its length. The resistance of a wire increases with its length. Suggest a relationship between the resistance of a wire and its length. Answer. The resistance of a wire is directly proportional to its length. Suggest a relationship for the resistance R and the length L. Answer. R is directly proportional to L. Click on the switch and observe the ammeter reading when a resistance wire of cross-sectional area 1.0 square millimeter is connected in the circuit. Click on each of the resistance wires of cross-sectional area 2.0 square millimeter and 3.0 square millimeter to connect it in the circuit. What happens to the current in the circuit when a wire of bigger cross-sectional area is used? Answer. The current increases. What can you deduce about the resistance of the wire of bigger cross-sectional area? Answer. Its resistance is lower. What is the relationship between the resistance R of a wire and its cross-sectional A? Answer. The resistance R is inversely proportional to its cross-sectional area. The resistance R of a wire of length L and cross-sectional area A is given by R equals ρ L over A, where ρ is known as the resistivity of the material of the wire. The unit for ρ is ohm meter. Click on each material in the table for the value of its resistivity at room temperature. Materials may be classified into one of three categories depending on their electrical resistivity. These are conductors, semiconductors, and insulators. All metals are good conductors. They have very low resistivity, whereas insulators like glass and rubber have very high resistivity. The resistivity of semiconductors is higher than that of metals, but lower than that of insulators. Click on the resistance of the wire is given by the equation text to go through the worked example. Summary. The resistance of a conductor is directly proportional to its length L of the conductor, but inversely proportional to its cross-sectional area A. Resistance R is given by R is proportional to L over A. R is equals to rho L over A, where rho is known as the resistivity of the material. Electrical conduction in a metal is due to the drift of free electrons. The free electrons drift in the direction opposite to that of the electric field. Conductivity sigma is the reciprocal resistivity. Sigma equals 1 over rho. Click the derivation button to observe the derivation of the expression for resistivity in terms of N and tau. The resistivity of a material depends. Conductivity sigma is the reciprocal resistivity. Sigma equals 1 over rho. Click the derivation button to observe the derivation of the expression for resistivity in terms of N and tau. The resistivity of a material depends on the temperature. Click the explanation button. Observe the drift of free electrons in a metal at a low temperature. Click on high temperature. What is the effect of the increase in the temperature on the electron drift? Answer. At a higher temperature, the ions vibrate with greater amplitude and frequency. The drift velocity of the free electrons decreases, hence the resistivity increases. Click and drag the slider to increase the temperature of a metal and observe the variation of its resistivity. Summary. The conductivity sigma of a material is related to the mean time tau between collisions by the formula sigma equals Ne squared tau over m. The resistivity ρ of a material is related to the mean time tau between collisions by the formula ρ equals 1 over sigma equals m over Ne squared tau, where n equals number of free electrons per unit volume, E equals charge of electron, m equals mass of electron. Resistivity ρ is the reciprocal of conductivity sigma. The resistivity of a metal increases when temperature increases because the increase in vibration of the metal ions impedes the drift of free electrons through the metal. The electrical conduction in a semiconductor is due to free electrons and positive holes. A positive hole is a vacancy left behind when an electron leaves its atom. Click the animation button. Click the play button to observe how holes conduct electricity in a semiconductor. An electron which is bound to an atom can move into a neighboring positive hole. The movement of the electron creates a hole. The hole appears to move in the direction of the electric field. Click and drag the slider to increase the temperature. What happens to the number of electron-hole pairs? Answer: the number of electron-hole pairs increases. How does the increase in temperature affect the resistivity and conductivity of the semiconductor? Answer: the resistivity decreases and the conductivity increases. Click and drag the slider to observe the variation of resistivity of a semiconductor with temperature. In addition to conductors, insulators, and semiconductors, there is another group of materials which exhibit extraordinary electrical properties. These materials are called superconductors. The maglev train uses superconductors to provide the strong magnetic forces required to levitate the train. Click and drag the slider to lower the temperature and observe the change in the resistivity of mercury. When the temperature of mercury drops below the critical temperature, Tc equals 4.2 Kelvin, its resistivity suddenly drops to zero. When the electrical resistance of a material becomes zero, the material exhibits the phenomenon known as superconductivity. The very low critical temperature of most materials to exhibit superconductivity was an obstacle to wide usage of superconductors in the early 20th century. Now, superconductors of critical temperature as high as 125 Kelvin made of ceramic materials have been developed. Click the Consequences button and the Applications button. Summary: in metals, the charge carriers are free electrons. In semiconductors, the charge carriers are free electrons and holes. Holes are considered as positive charge carriers. When the temperature of a semiconductor increases, the number of charge carriers per unit volume increases, hence the resistivity of the semiconductor decreases. A superconductor is a material that exhibits zero resistivity below its critical temperature, Tc. Different superconducting materials have different critical temperatures.